15.3 billion miles away from Earth. A machine the size of a small car is hurtling through the absolute darkness of interstellar space at 38,000 miles per hour. Voyager 1 has been traveling for over 46 years, and it's still moving. To put this distance in perspective, if you could drive a car at highway speeds for 24 hours a day without stopping, it would take you over 2,300 years to cover the same distance that Voyager 1 has traveled. We thought the moon was far away at 240,000 miles. We thought Mars was distant at 140 million miles. Voyager 1 has traveled a distance so vast that light from our sun takes over 22 hours to reach it. For decades, we believed that our solar system had clear boundaries, that there was a definite edge where our sun's influence ended and the great void of interstellar space began. We were completely wrong. In 2012, after traveling for 35 years, Voyager 1 crossed into a realm that no human-made object had ever entered before. True interstellar space. But here is what makes this achievement almost impossible to comprehend. Voyager 1 didn't just stumble into this cosmic milestone by accident. Every mile of its 15 billion mile journey was planned, calculated, and executed with precision that required predicting the positions of planets years in advance. The numbers behind Voyager 1's journey are staggering. It has traveled a distance equivalent to circling Earth's equator 614,000 times. If you lined up every mile of its journey in $1 bills, they would stretch from Earth to the moon and back again 32 times. The spacecraft has been traveling for so long that children born when it launched are now approaching retirement age. Yet Voyager 1 is still transmitting data back to Earth from the edge of our solar system. Scientists initially thought Voyager 1's primary mission would last 4 years. They planned for encounters with Jupiter and Saturn, expecting the spacecraft to complete its observations and fade into the cosmic background as a silent monument to human ambition. Instead, Voyager 1 became the little engine that could of space exploration, continuing to operate and make discoveries for over a decade beyond its planned lifespan. Here is where the story becomes truly extraordinary. Voyager 1 achieved this incredible distance not through raw power or massive fuel reserves, but through a cosmic dance with the gravity of giant planets. The spacecraft weighs only 1,590 pounds, less than a small car, yet it used the gravitational fields of Jupiter and Saturn as cosmic slingshots, gaining speed with each planetary encounter until it reached velocities that no amount of rocket fuel could have provided. Dr. Edward Stone, Voyager's project scientist since 1972, describes the magnitude of this achievement. When we launched Voyager 1 in 1977, we were essentially throwing a message in a bottle into a cosmic ocean, hoping it would reach shores we had never seen. Not only did it reach those shores, but it sent back detailed reports of everything it encountered along the way. The journey to 15 billion miles required solving engineering challenges that pushed 1970s technology to its absolute limits. Voyager 1 carries a computer with less processing power than a modern calculator, operates on electrical power equivalent to a bright light bulb, and communicates with Earth using a radio transmitter weaker than a cell phone. Yet this modest collection of 1970s electronics has functioned flawlessly in the harsh environment of space for nearly half a century. But perhaps the most mind-bending aspect of Voyager 1's 15 billion mile journey is what it reveals about the true scale of our cosmic neighborhood. When Voyager 1 crossed into interstellar space after 35 years of travel, it had barely begun to leave our solar system's sphere of influence. The spacecraft won't approach another star system for over 40,000 years, and it will take over 300 years for Voyager 1 to travel the distance from the Sun to the nearest star. Tonight, we're following Voyager 1's incredible journey from its launch on September 5, 1977, to its current position as humanity's most distant ambassador. You will discover how NASA engineers use the rare alignment of planets that occurs only once every 175 years, learn about the revolutionary discoveries that changed our understanding of the outer solar system, and explore the technical challenges of maintaining communication with a spacecraft that is 3 times farther from Earth than Pluto. We'll investigate the precise gravitational maneuvers that allowed a spacecraft, launched with 1970s technology, to achieve speeds that modern rockets cannot match. Examine the scientific instruments that are still making groundbreaking discoveries after 46 years in space, and uncover the profound implications of Voyager 1's journey for our understanding of humanity's place in the cosmos. You'll learn about the golden record attached to Voyager 1, a message intended for any intelligent life that might discover the spacecraft millions of years in the future, and understand how this small spacecraft became a time capsule carrying Earth's story into the infinite darkness between the stars. We'll explore what Voyager 1's instruments are detecting in interstellar space, and how these measurements are revealing the true nature of the space between star systems. This isn't just a story about a remarkable engineering achievement. This is about humanity's first tentative step into the galaxy. A journey that began with ambitious dreams in the 1970s and continues today as Voyager 1 sends back data from regions of space no human will visit for centuries to come. The distance of 15 billion miles represents more than just a number. It represents the farthest humanity has ever extended its reach into the cosmos. As we follow Voyager 1's incredible journey, we're also tracing the evolution of our species from a planet-bound civilization to one with permanent presence in interstellar space, even if that presence is currently limited to a single robotic explorer carrying our hopes and curiosity into the unknown. If you're fascinated by humanity's greatest journey of exploration, subscribe and hit the thumbs up button. And here is a question that will change how you think about distance forever. If Voyager 1 continues at its current speed, how long would it take to reach the center of our galaxy? Comment below with your calculations. I'll pin the most accurate answer. Now, let's begin our journey alongside Voyager 1, following humanity's most distant messenger as it travels through the cosmic ocean that separates our solar system from the stars. Chapter 1: Grand Vision. The story of Voyager 1's 15 billion-mile journey begins not with rockets or spacecraft, but with a rare cosmic alignment that occurs only once every 175 years. In the early 1960s, a young graduate student named Gary Flandreau was working at NASA's Jet Propulsion Laboratory calculating planetary trajectories for future missions when he discovered something that would revolutionize space exploration. The outer planets of our solar system were moving into an almost perfect alignment that would allow a single spacecraft to visit multiple worlds using gravitational assists. Flandreau's calculations revealed that between 1976 and 1980, Jupiter, Saturn, Uranus, and Neptune would align in a configuration that hadn't occurred since Thomas Jefferson was president. This alignment meant that a spacecraft launched during this narrow window could use the gravity of each planet to accelerate toward the next, like a cosmic pinball machine where each collision increased the spacecraft's velocity rather than slowing it down. The concept of gravitational assist wasn't new. It had been proposed by Italian mathematician Giuseppe Colombo and Russian engineer Yuri Kondratyuk decades earlier. But Flandreau was the first to recognize that the upcoming planetary alignment would allow what he called the Grand Tour, a single mission that could visit all 4 gas giant planets for the first time in human history. Dr. Bruce Murray, who directed the Jet Propulsion Laboratory during the Voyager program's development, later described Flandreau's discovery as the key that unlocked the outer solar system. Without the gravitational assist technique, reaching the outer planets would require spacecraft with fuel tanks larger than entire buildings, making interplanetary exploration economically impossible with 1970s technology. The Grand Tour concept immediately captured NASA's imagination, but it also presented unprecedented challenges. Previous space missions had lasted months or at most a few years. The Grand Tour would require spacecraft to operate reliably for over a decade, while traveling billions of miles from Earth through environments that had never been directly explored. Every component would need to function perfectly in the extreme cold of deep space, withstand intense radiation near Jupiter, and maintain communication across distances that stretched the limits of radio technology. NASA's initial Grand Tour proposal was ambitious beyond anything previously attempted. The plan called for launching 4 spacecraft, 2 in 1977 to visit Jupiter, Saturn, and Pluto, and 2 more in 1979 to explore Jupiter, Uranus, and Neptune. The total cost was estimated at $750 million, equivalent to over $4 billion today, making it one of the most expensive robotic space missions ever proposed. Congress balked at the enormous expense, forcing NASA to scale back the Grand Tour concept. In 1972, the agency approved a more modest mission called Mariner Jupiter-Saturn, which would launch 2 spacecraft to explore only the 2 innermost gas giants. But NASA engineers, led by project manager John Cassani, secretly designed the spacecraft with capabilities far beyond what the scaled-back mission required. The engineers equipped both spacecraft with instruments capable of studying all 4 gas giants' power systems, designed to operate for decades rather than years, and communication systems optimized for the vast distances they would encounter if their missions were extended beyond Saturn. This forward-thinking approach would prove crucial when the spacecraft performed so well that NASA approved mission extensions that transformed a 4-year mission into a decades-long exploration of the outer solar system. Voyager 1 and Voyager 2. The names were adopted in 1977 to reflect their expanded mission scope, were marvels of 1970s engineering designed to push technology to its absolute limits. Each spacecraft weighed 1,590 pounds and stood 8.5 feet tall, with a distinctive high-gain antenna that resembled a large dish aimed toward Earth for communication. The spacecraft were powered by 3 radioisotope thermoelectric generators, RTGs, that converted heat from decaying plutonium-238 into electricity, providing power that would remain stable for decades. The scientific instrument package represented the most sophisticated remote sensing laboratory ever assembled for space exploration. Voyager 1 carried 11 different experiments designed to study planetary atmospheres, magnetic fields, charged particles, cosmic rays, and radio emissions. The cameras, built by the same company that manufactured television equipment, could capture images with resolution far superior to Earth-based telescopes while operating in the harsh environment of deep space. But perhaps the most remarkable aspect of Voyager 1's design was its computer system, a masterpiece of compact engineering that stored its operating instructions on digital tape recorders. The spacecraft's main computer had just 4,096 words of memory and operated at a clock speed of 250,000 cycles per second, roughly 25,000 times slower than a modern smartphone. Yet this modest computer was designed to control every aspect of the spacecraft's operation, while making autonomous decisions during the long communication delays inevitable when operating billions of miles from Earth. The trajectory planning for Voyager 1's Grand Tour required calculations of unprecedented precision. Engineers needed to predict the exact positions of planets years in advance, accounting for gravitational influences from every significant body in the solar system. The launch window for optimal trajectory was incredibly narrow, just 20 days when the planets would be aligned correctly for the gravitational assist sequence to work. Dr. Charlie Colhase, who led the mission design team, spent years calculating trajectories with slide rules and early computers, mapping every possible path through the outer solar system. His team discovered that Voyager 1 could gain over 35,000 miles per hour of velocity through gravitational assists, more than doubling its speed and reducing the travel time to Saturn from 11 years to just 3 years. The gravitational assist technique works by having a spacecraft approach a planet from behind in its orbital motion around the Sun. As the spacecraft falls into the planet's gravitational well, it gains speed. If the encounter is designed correctly, the spacecraft can be flung out of the gravitational well with more energy than it entered, effectively stealing orbital energy from the planet and adding it to the spacecraft's velocity. The energy gain is tiny compared to the planet's total orbital energy. Jupiter loses only about 1 part in 1020 of its orbital energy when accelerating a Voyager spacecraft. But for the spacecraft, the velocity increase is enormous, providing speed that would be impossible to achieve with conventional rocket propulsion, given the weight limitations of 1970s launch vehicles. The timing requirements for gravitational assists were extraordinarily demanding. Voyager 1 needed to arrive at Jupiter at precisely the right moment to be flung towards Saturn at the correct angle and velocity. The margin for error was measured in minutes across a journey lasting years, requiring navigation accuracy equivalent to hitting a target the size of a building from a distance of 1,000 miles. NASA's decision to proceed with the Voyager missions represented a profound leap of faith in human technological capability. The agency was committing to a mission that would extend far beyond the careers of most of the engineers who designed it, betting that 1970s technology could operate reliably in environments that had never been directly studied. The spacecraft would need to function autonomously for years at a time, making critical decisions about instrument operations and data collection while Earth-based controllers waited hours for radio signals to cross the vast distances of interplanetary space. The Grand Tour concept transformed space exploration from a series of individual planetary visits into a systematic survey of the outer solar system. Previous missions had provided tantalizing glimpses of worlds like Jupiter and Saturn, but Voyager promised detailed scientific investigations that would revolutionize our understanding of planetary formation, atmospheric dynamics, and the complex interactions between planets and their moons. As launch preparations intensified in 1977, the Voyager team realized they were embarking on a journey that would define humanity's relationship with the cosmos for generations to come. The spacecraft weren't just scientific instruments, they were ambassadors, carrying human curiosity and technological achievement to regions of space that no human would visit for centuries, if ever. The vision of the Grand Tour represented humanity at its most optimistic and ambitious, committing resources and expertise to a project whose benefits would extend far beyond the political and technological concerns of the 1970s. Voyager 1's 15 billion-mile journey began with this grand vision of systematic exploration, a dream of understanding our cosmic neighborhood that would drive human achievement to unprecedented heights and forever change our perspective on our place in the universe. Chapter 2. Launch window September 5th, 1977. Dawn clear and humid at Cape Canaveral, Florida. But the perfect weather couldn't mask the extraordinary tension surrounding Voyager 1's launch. After years of planning, engineering, and political battles, NASA had just 20 days to launch both Voyager spacecraft during the narrow window when planetary alignment would allow the Grand Tour trajectory. Missing this opportunity would mean waiting 175 years for another chance, longer than the United States had existed as a nation. The launch sequence began before sunrise as technicians performed final checks on the Titan III Centaur rocket, a massive 3-stage vehicle standing 160 feet tall and weighing 1.4 million pounds when fully fueled. The Titan III was one of the most powerful rockets available in 1977, but even this enormous launcher could barely provide enough energy to send Voyager 1 on its journey to Jupiter. Every pound of weight had been scrutinized, every component optimized for the demanding mission ahead. Dr. John Cassani, Voyager's project manager, spent the final hours before launch in NASA's Mission Control Center, monitoring hundreds of systems that all needed to function perfectly for the mission to succeed. The complexity was staggering. The spacecraft contained over 65,000 individual parts, each manufactured to tolerances measured in thousandths of an inch, all designed to operate in the harsh environment of space for far longer than any previous mission had attempted. The launch window opened at 8:56 a.m. Eastern Time, but a series of minor technical delays pushed the actual launch to 12:56 p.m. as the countdown reached its final seconds. Kasani and his team knew they were committing an irreplaceable piece of human technology to a journey that would last longer than most human lifetimes. There would be no opportunity for repairs, no chance to upgrade components, no possibility of bringing Voyager 1 home if something went wrong. At 12 hours 56 minutes and 0 seconds p.m. precisely, the Titan E's and main engines ignited with a thunderous roar that could be heard for miles across the Florida coast. The rocket lifted slowly at first, fighting against Earth's gravity with 2.4 million pounds of thrust. Within seconds, Voyager 1 was accelerating through the atmosphere at speeds that would carry it completely beyond Earth's gravitational influence for the first time in human history. The launch sequence unfolded exactly as planned across 3 carefully choreographed stages. The solid rocket boosters burned for 2 minutes, providing the initial thrust needed to escape Earth's atmosphere. The Titan's second stage fired for another 6 minutes, accelerating Voyager 1 to orbital velocity. Finally, the Centaur upper stage completed 2 burns, first to achieve a parking orbit around Earth, then to accelerate Voyager 1 to the 36,000 miles per hour needed to escape Earth's gravity entirely. 43 minutes after launch, Voyager 1 separated from the Centaur stage and began its independent journey toward Jupiter. The spacecraft immediately oriented itself using its star trackers, locking onto the bright star Canopus as a reference point and deploying its scientific instruments for the long journey ahead. For the first time since humans began looking up at the night sky, one of our creations was traveling toward another world with the capability to send back detailed observations of what it discovered. The timing of Voyager 1's launch was not arbitrary. It was the culmination of years of precise calculations that took into account the orbital mechanics of planets, the performance characteristics of the launch vehicle, and the optimal trajectory for reaching Jupiter at exactly the right moment for a gravitational assist toward Saturn. Launch just 1 day too early or too late would have meant missing Jupiter entirely or arriving at the wrong angle for the critical gravity assist maneuver. Dr. Charlie Colhess, who designed Voyager 1's trajectory, had calculated that the spacecraft needed to reach Jupiter in March 1979, exactly 18 months after launch. This required maintaining an average speed of over 35,000 miles per hour across the 400 million mile journey, a pace that demanded extraordinary precision in the initial launch trajectory. Even tiny errors in the launch velocity would compound over months of travel, potentially causing the spacecraft to miss Jupiter by millions of miles. The first critical milestone came just 4 days after launch when Voyager 1's high-gain antenna successfully locked onto the Deep Space Network stations on Earth. The radio signal, traveling at the speed of light, took only seconds to cross the distance between Earth and the spacecraft. But as Voyager 1 continued its journey toward Jupiter, these communication delays would gradually increase until eventually it would take over 20 hours for signals to travel between Earth and the spacecraft. Within weeks of launch, Voyager 1 was already making its first scientific observations. The spacecraft's cosmic ray detectors began measuring high-energy particles streaming from the Sun, while its magnetometer mapped the complex structure of Earth's magnetic field as seen from interplanetary space. These early measurements confirmed that all of Voyager 1's scientific instruments were functioning perfectly, validating years of careful engineering and testing. The trajectory toward Jupiter required only minor course corrections during the first year of flight. NASA's navigation team tracked Voyager 1's position using radio ranging techniques that measured the spacecraft's distance to within a few miles across hundreds of millions of miles. These precise measurements allowed engineers to predict exactly where Voyager 1 would be months in advance, enabling them to plan instrument observations and prepare for the complex Jupiter encounter sequence. As 1977 turned into 1978, Voyager 1 crossed the orbit of Mars and entered the asteroid belt, a region of space that many scientists feared might be too hazardous for spacecraft passage. The belt contains millions of rocky fragments ranging from dust particles to objects hundreds of miles across, all orbiting the Sun in the region between Mars and Jupiter. Previous missions had successfully transited the asteroid belt, but Voyager 1 was the most complex and valuable spacecraft ever to attempt the passage. The asteroid belt crossing proved uneventful. Space is so vast that even the crowded asteroid belt consists primarily of empty vacuum. Voyager 1 passed through the belt without encountering any significant debris, confirming that interplanetary space was safe for future missions to the outer solar system. This successful passage opened the door for dozens of subsequent missions that would follow Voyager's pioneering path. By early 1979, Voyager 1 was approaching Jupiter at ever-increasing speed as the giant planet's gravitational field began to accelerate the spacecraft. The excitement at NASA was palpable. After 18 months of travel through the relative emptiness of interplanetary space, Voyager 1 was about to provide humanity's first close-up look at the largest planet in our solar system and its complex system of moons. The approach to Jupiter revealed the true magnitude of what NASA had achieved. Voyager 1 was operating flawlessly after 18 months in space. Its instruments were functioning perfectly, and its trajectory was so precise that only minimal course corrections were needed to achieve the optimal Jupiter flyby geometry. The spacecraft was about to begin the scientific observations that would transform our understanding of planetary formation and dynamics. Dr. Edward Stone, Voyager's chief scientist, assembled a team of over 100 researchers from universities and laboratories around the world to analyze the data that Voyager 1 would collect during its Jupiter encounter. This represented the largest coordinated planetary science investigation ever attempted, bringing together experts in atmospheric dynamics, magnetospheric physics, geology, and chemistry to interpret observations from an alien world. The launch window that began with such tension and uncertainty had delivered humanity's most ambitious space mission exactly where it needed to be, there. Voyager 1's successful journey to Jupiter validated the grand tour concept and demonstrated that human technology could operate reliably across the vast distances of interplanetary space. The 15 billion-mile journey that would make Voyager 1 humanity's most distant messenger began with this perfect launch, setting in motion a sequence of discoveries that would continue for decades to come. The success of Voyager 1's launch and early mission phases represented a triumph of human planning, engineering, and determination. From the initial recognition of the planetary alignment opportunity to the flawless execution of launch and interplanetary cruise, every aspect of the mission demonstrated humanity's growing capability to explore the cosmos beyond Earth's immediate neighborhood. As Voyager 1 approached Jupiter in early 1979, the spacecraft was about to begin the most intensive phase of its primary mission. But unknown to the scientists and engineers who had devoted years of their lives to making this moment possible, the Jupiter encounter would prove to be just the first chapter in a journey that would extend far beyond anyone's wildest expectations, ultimately carrying Voyager 1 to the edge of interstellar space and making it humanity's first ambassador to the galaxy. Chapter 3. Jupiter Encounter. On March 5, 1979, Voyager 1 reached its closest approach to Jupiter, passing just 174,000 miles above the giant planet's cloud tops at a relative velocity of 70,000 miles per hour. This moment represented the culmination of humanity's most ambitious space mission. As our most sophisticated robotic explorer began transmitting the first detailed observations of an alien world that dwarfed everything in human experience. What Voyager 1 discovered during its 4-month Jupiter encounter fundamentally changed our understanding of planetary formation, atmospheric dynamics, and the possibility of life in the outer solar system. The scale of Jupiter immediately challenged human comprehension. Voyager 1's images revealed a world so massive that over 1,300 Earths could fit inside its volume, with atmospheric dynamics operating on scales that dwarfed terrestrial weather systems. The Great Red Spot, a storm that had been observed from Earth for centuries as a small reddish feature, was revealed to be a hurricane-like vortex larger than Earth itself, with wind speeds exceeding 250 miles per hour that had been sustained for at least 300 years. Dr. Andrew Ingersoll from the California Institute of Technology, who led Voyager 1's atmospheric studies, was stunned by the complexity of Jupiter's weather systems. The spacecraft's images revealed intricate bands of clouds stretching around the planet, with jet streams flowing at different velocities and creating turbulent interactions that generated dozens of smaller storm systems. "We thought we understood atmospheric dynamics from studying Earth's weather," Ingersoll later recalled. "But Jupiter operates on completely different principles that challenged everything we thought we knew about how atmospheres behave." Voyager 1's infrared spectrometer revealed that Jupiter was actively generating heat, radiating 2.5 times more energy than it receives from the Sun. This internal heat source, created by gravitational compression as the planet slowly contracts under its own massive gravity, drives the complex atmospheric circulation that creates Jupiter's distinctive banded appearance. The discovery confirmed that Jupiter is almost a failed star. If it had been about 80 times more massive, nuclear fusion would have ignited in its core, creating a binary star system in place of our solar system. But perhaps the most revolutionary discovery came when Voyager 1 turned its cameras toward Io, one of Jupiter's 4 largest moons. Scientists expected to find a cold, cratered world similar to Earth's moon, but instead discovered a bizarre landscape painted in vivid yellows, oranges, and reds. As Voyager 1, as navigation engineer, Linda Morabito was processing images to help determine the spacecraft's precise position. She noticed something extraordinary: a crescent-shaped plume of material extending 190 miles above Io's surface. The discovery of volcanic activity on Io revolutionized planetary science overnight. Here was a moon only slightly larger than Earth's moon, yet actively erupting with volcanoes more powerful than anything on Earth. Voyager 1's images revealed at least 8 active volcanoes on Io's surface, with some eruptions launching material at velocities exceeding 2,000 miles per hour, fast enough to escape Io's gravity and form a donut-shaped ring of particles around Jupiter. Dr. Bradford Smith, who led Voyager's imaging team, described the moment of discovery. "We were looking at a world that was turning itself inside out through volcanic activity powered by forces we barely understood. Io's surface was so young and active that we were essentially watching a moon recreate itself, through geological processes operating at speeds millions of times faster than anything on Earth." The source of Io's volcanic energy proved to be tidal heating caused by Jupiter's enormous gravitational field. As Io orbits Jupiter in an elliptical path influenced by the other major moons, the changing gravitational forces continuously flex and squeeze the moon's interior, generating heat through friction. This process produces enough energy to melt Io's interior and drive the most volcanically active world in the solar system. Voyager 1's magnetometer revealed another stunning discovery. Jupiter possesses a magnetic field 20,000 times stronger than Earth's, extending millions of miles into space and trapping high-energy particles in radiation belts so intense they would be lethal to humans within minutes. The spacecraft itself was damaged by Jupiter's radiation environment, with some of its electronics degraded by exposure to particle fluxes far exceeding the most extreme conditions found near Earth. The radiation belts surrounding Jupiter were populated with sulfur and oxygen ions stripped from Io's volcanic eruptions, creating a complex plasma environment that extends throughout the Jupiter system. Voyager 1's plasma wave instrument detected radio emissions generated by the interaction between Io's volcanic particles and Jupiter's magnetic field, revealing that moons could actively influence the magnetic environments of their parent planets. Europa, another of Jupiter's major moons, presented a completely different mystery. Voyager 1's images revealed a surface covered in a network of linear features that resembled cracks in ice, with very few impact craters visible. The smooth, young appearance of Europa's surface suggested that geological processes were actively erasing crater formation, possibly through the movement of a global ocean beneath the moon's icy surface. Dr. Robert Pappalardo, who analyzed Voyager 1's Europa images, recognized that the linear features could be explained by tidal flexing similar to what drives Io's volcanism, but operating on a world where water rather than rock was being heated and mobilized. The possibility that Europa might harbor a liquid ocean beneath its icy surface opened entirely new possibilities for life in the outer solar system, in environments completely unlike anything found on Earth. Ganymede, Jupiter's largest moon, revealed evidence of a complex geological history with both heavily cratered, ancient terrain and younger regions with parallel ridges and valleys. The dichotomy suggested that Ganymede had experienced periods of intense geological activity separated by billions of years of relative quiet, providing clues about how large moons evolve over solar system history. Callisto, the most heavily cratered of Jupiter's major moons, showed evidence of impact events so catastrophic they created multi-ring basin structures hundreds of miles across. These ancient scars provided a record of the intense bombardment that characterized the early solar system, when planetary formation was still actively occurring through collisions between large rocky bodies. Voyager 1's discoveries at Jupiter extended far beyond the planet and its major moons. The spacecraft detected a faint ring system around Jupiter, consisting of tiny particles probably created by micrometeorite impacts on Jupiter's innermost moons. This ring system was completely unexpected. Before Voyager 1, only Saturn was known to have rings, and the discovery suggested that ring systems might be common features of the giant planets. The 4-month Jupiter encounter generated more scientific data than all previous planetary missions combined. Voyager 1 transmitted over 19,000 images and collected measurements from 11 different scientific instruments operating simultaneously, creating the most comprehensive survey of an alien world ever attempted. The data required years of analysis by hundreds of researchers working to understand the complex interactions between Jupiter's atmosphere, magnetosphere, and moons. The gravitational assist maneuver that concluded Voyager 1's Jupiter encounter worked exactly as planned, accelerating the spacecraft from 70,000 to over 100,000 miles per hour while precisely targeting its trajectory towards Saturn. The gravity assist was so accurate that only minor course corrections were needed to ensure optimal arrival at Saturn 20 months later. Jupiter's gravity had provided Voyager 1 with velocity that would have been impossible to achieve with any conceivable rocket, demonstrating the power of celestial mechanics to enable ambitious space exploration. As Voyager 1 departed the Jupiter system in April 1979, it carried with it a revolutionary new understanding of how planets and moons form and evolve. The discoveries of active volcanism on Io, possible oceans on Europa, and complex atmospheric dynamics on Jupiter revealed that the outer solar system was far more dynamic and interesting than anyone had imagined. These worlds weren't just cold, dead objects orbiting in the outer darkness. They were active, evolving systems with their own geological processes, and possibly even the potential for life. The success of Voyager 1's Jupiter encounter validated the Grand Tour concept and demonstrated that robotic spacecraft could successfully explore the outer solar system with instruments sensitive enough to make fundamental discoveries about alien worlds. The mission's achievements at Jupiter generated enormous public excitement and political support for continuing Voyager 1's journey to Saturn and beyond. Dr. Edward Stone summarized the significance of the Jupiter encounter. In 4 months, Voyager 1 taught us more about Jupiter than we had learned in the previous 4 centuries of telescopic observation. We discovered that the outer solar system contained worlds as complex and dynamic as Earth itself, with geological processes, atmospheric systems, and possibly even conditions suitable for life operating on scales and through mechanisms we had never imagined possible. The Jupiter encounter marked the beginning of Voyager 1's transformation from a planned 4-year mission into a decades-long exploration that would eventually carry the spacecraft 15 billion miles from Earth. But in 1979, as Voyager 1 headed towards Saturn with its instruments still functioning perfectly and its trajectory precisely on target, the focus was on preparing for the next phase of discoveries that awaited in the ring planet system. Chapter 4: Saturn's Secrets. On November 12, 1980, Voyager 1 reached its closest approach to Saturn, passing within 78,000 miles of the ring planet's cloud tops and beginning an encounter that would revolutionize our understanding of planetary ring systems while revealing one of the most Earth-like worlds in the solar system. What Voyager 1 discovered during its Saturn flyby challenged fundamental assumptions about how rings form and evolve, while uncovering evidence for complex organic chemistry occurring on a moon that might harbor conditions suitable for life. Saturn had captivated astronomers since Galileo first observed its strange, elongated appearance through his primitive telescope in 1610. For centuries, Saturn's rings remained a beautiful but poorly understood phenomenon, a thin, flat structure that seemed to defy the gravitational forces that should have caused it to either collapse onto the planet or disperse into space. Voyager 1's close-up observations revealed that Saturn's rings were far more complex and dynamic than anyone had imagined. The spacecraft's images showed that Saturn's seemingly smooth rings were actually composed of thousands of individual ringlets, each following its own orbital path around the planet. Dr. Bradford Smith, leader of Voyager's imaging team, described the revelation. "We expected to find perhaps a dozen major ring divisions, but instead discovered a structure as complex as a phonograph record with thousands of individual grooves maintained by gravitational forces operating with extraordinary precision." Voyager 1's radio science experiment provided the most detailed measurement of ring structure ever attempted. As the spacecraft passed behind Saturn relative to Earth, radio signals transmitted from Earth passed through the rings before reaching Voyager 1's receiver. The wavy radio signals were absorbed and scattered by ring particles, revealed the detailed structure and composition of the ring system with resolution measured in feet rather than miles. The radio occultation measurements revealed that Saturn's rings are incredibly thin relative to their diameter, typically less than 30 feet thick despite spanning over 170,000 miles from edge to edge. This thinness ratio is equivalent to a sheet of paper scaled to the size of a football field, demonstrating the extraordinary precision with which gravitational forces organize ring particles into stable orbital configurations. Perhaps most surprisingly, Voyager 1 discovered that Saturn's rings are composed almost entirely of water ice, ranging in size from tiny snowflakes to house-sized boulders. The purity of this ice suggested that the rings are relatively young in solar system terms, probably less than 100 million years old compared to the 4.6 billion year age of the solar system itself. This discovery implied that ring systems are temporary features that form and dissipate over geological timescales. The spacecraft detected mysterious spoke-like features in Saturn's rings that appeared and disappeared over periods of hours. These spokes seemed to defy orbital mechanics. They maintained their shape despite being composed of particles that should have moved at different speeds. According to Kepler's laws, Dr. Carolyn Porco, who studied the spoke phenomena, determined that they were created by electromagnetic effects that temporarily levitated tiny ring particles above the main ring plane. Voyager 1's encounter with Titan, Saturn's largest moon, provided one of the mission's most significant discoveries. Titan had long been known to possess an atmosphere, but ground-based observations suggested it was thin and composed primarily of hydrogen. Voyager 1's instruments revealed that Titan's atmosphere is actually thicker than Earth's, with surface pressure 50% higher than at Earth's sea level, composed primarily of nitrogen with significant amounts of methane and complex organic compounds. The thick atmosphere completely obscured Titan's surface from optical observation, but Voyager 1's infrared instruments penetrated the haze to reveal tantalizing glimpses of surface features. Temperature measurements indicated that despite receiving only 1% of the sunlight that reaches Earth, Titan's thick atmosphere creates a greenhouse effect that maintains surface temperatures around -290 degrees Fahrenheit, cold by Earth standards, but warm enough for complex chemistry involving methane and other organic compounds. Dr. Tobias Owen, who analyzed Voyager 1's atmospheric measurements, recognized that Titan possessed the most Earth-like atmosphere found anywhere in the solar system. The combination of nitrogen, organic compounds, and possible surface liquids created conditions remarkably similar to Earth's primitive atmosphere billions of years ago. Titan appeared to be a frozen laboratory where we could study the same chemical processes that might have led to life on Earth, Owen explained. The discovery of complex organic chemistry in Titan's atmosphere immediately elevated the Moon's importance for astrobiology research. Voyager 1's mass spectrometer detected hydrogen cyanide, acetylene, ethylene, and other organic compounds that serve as building blocks for more complex molecules essential to life. The chemistry occurring in Titan's atmosphere represented the most complex organic processes known to exist anywhere in the solar system beyond Earth. Voyager 1's infrared measurements suggested that Titan's surface might contain lakes or seas of liquid methane and ethane, creating an environment where organic chemistry could proceed through mechanisms completely unknown on Earth. The possibility that liquid hydrocarbons might exist on Titan's surface opened entirely new avenues for understanding how chemistry evolves in extraterrestrial environments. The spacecraft's magnetometer revealed that Saturn possesses a magnetic field almost perfectly aligned with its rotational axis, a unique configuration among the giant planets that challenged theories about how planetary magnetic fields form. The precision of this alignment, to within less than 1 degree, suggested that Saturn's magnetic field generation involves physical processes different from those operating on other planets. Voyager 1 discovered several new moons orbiting Saturn, including small, irregularly shaped objects embedded within the ring system itself. These shepherd moons were found to gravitationally confine ring particles through complex resonance effects, explaining how narrow rings could maintain their sharp edges over millions of years. The discovery revealed that Saturn's moons and rings form an integrated dynamic system where gravitational interactions continuously reshape both the ring structure and moon orbits. Enceladus, one of Saturn's smaller icy moons, exhibited a surprisingly young and varied surface with evidence of recent geological activity. Some regions showed heavy cratering typical of ancient surfaces, while others appeared almost crater-free, suggesting active resurfacing processes. The geological activity was puzzling because Enceladus seemed too small to maintain internal heat sources through radioactive decay or tidal heating. Iapetus, Saturn's third-largest moon, presented one of the most bizarre discoveries of the entire Saturn encounter. Voyager 1's images revealed that one hemisphere of Iapetus is 6 times brighter than the other, creating a two-toned world with dramatic color contrasts visible from millions of miles away. The dark material appeared to be concentrated on the hemisphere that faces forward in Iapetus's orbit, suggesting that the moon was sweeping up dark particles from space. The gravitational assist maneuver at Saturn provided Voyager 1 with additional velocity, while precisely targeting its trajectory to depart the Saturn system at the optimal angle for continued exploration. However, unlike the Jupiter encounter, which provided a direct path to the next planet, the Saturn assist sent Voyager 1 on a trajectory that would take it out of the ecliptic plane, the flat disk containing most planetary orbits, and toward interstellar space. This trajectory choice represented a crucial decision point for the Voyager mission. NASA could have used the Saturn gravity assist to send Voyager 1 toward Uranus and Neptune, but mission planners chose instead to optimize the spacecraft's path for a close encounter with Titan. This decision meant that Voyager 1 would not visit any additional planets, but it enabled the detailed study of Titan that revealed the moon's extraordinary atmosphere and organic chemistry. The Saturn encounter generated over 16,000 images and vast amounts of data from Voyager 1's 11 scientific instruments. The complexity of Saturn's ring system required entirely new theoretical models to explain how gravitational forces could maintain such intricate structures over millions of years. The discoveries challenged fundamental assumptions about planetary formation and the evolution of satellite systems. Dr. Edward Stone reflected on the significance of Voyager 1's Saturn discoveries. Saturn taught us that the outer solar system contains worlds and phenomena far more complex and interesting than we had imagined. From the intricate dynamics of ring systems to the possibility of prebiotic chemistry on Titan, Saturn revealed that every world in our cosmic neighborhood has its own unique story to tell about planetary formation and evolution. As Voyager 1 departed the Saturn system in November 1980, the spacecraft was beginning the longest phase of its journey. With no more planetary encounters planned, Voyager 1 would spend the next 3 decades traveling through the outer reaches of the solar system, gradually approaching the boundary where our sun's influence gives way to interstellar space. The discoveries at Saturn had demonstrated that even with 1970s technology, robotic explorers could revolutionize our understanding of alien worlds, setting the stage for the extended mission that would ultimately carry Voyager 1 to the edge of our solar system and beyond. The Saturn encounter marked the end of Voyager 1's primary mission, but it was also the beginning of an unexpected journey that would continue for decades, eventually making the spacecraft humanity's first messenger to interstellar space. The success at Saturn validated the Grand Tour concept while opening entirely new questions about planetary formation, atmospheric evolution, and the potential for life in environments completely unlike Earth. Chapter 5: Gravity's Gift: The Gravitational Assist Maneuvers That Enabled Voyager 1's journey to 15 billion miles represent one of the most elegant applications of celestial mechanics in the history of space exploration. Without these precisely calculated encounters with Jupiter and Saturn, Voyager 1 would have required fuel tanks larger than entire buildings to achieve the velocities needed for its extended mission. Understanding how gravity assists work reveals the extraordinary precision required to navigate the solar system, using the planets themselves as cosmic accelerators. The fundamental principle behind gravitational assists, also known as gravity assists or slingshot maneuvers, relies on the conservation of energy and momentum in gravitational encounters. When a spacecraft approaches a planet, it falls into the planet's gravitational well, gaining speed as gravitational potential energy converts to kinetic energy. If the encounter geometry is designed correctly, the spacecraft can be flung out of the gravitational well with more speed than it entered, effectively stealing orbital energy from the planet. Dr. Michael Minovich, who developed a mathematical foundation for gravitational assists while working at NASA's Jet Propulsion Laboratory in the 1960s, explained the energy transfer mechanism. A spacecraft approaching a planet from behind in the planet's orbital motion can gain enormous amounts of velocity by riding along with the planet's motion around the sun. It is like jumping onto a moving train. You gain the train's velocity in addition to your own running speed. The energy gain is possible because planets are moving at tremendous velocities in their orbits around the Sun. Jupiter orbits at approximately 29,000 miles per hour, while Saturn moves at about 21,000 miles per hour. When a spacecraft encounters these planets from the optimal approach angle, it can gain significant fractions of these orbital velocities, providing acceleration that would be impossible to achieve through rocket propulsion alone. Voyager 1's Jupiter encounter on March 5, 1979, provided a velocity increase of approximately 35,000 miles per hour, more than doubling the spacecraft's speed relative to the Sun. This acceleration reduced Voyager 1's travel time to Saturn from 11 years to just 20 months, while providing the energy needed to eventually escape the solar system entirely. The gravity assist was so effective that it provided more velocity than Voyager 1's initial launch from Earth. The precision required for successful gravity assists challenges human comprehension. Mission planners must predict the exact positions of planets months or years in advance, accounting for gravitational influences from every significant body in the solar system. The approach trajectory must be calculated to within fractions of a degree to achieve the desired exit velocity and direction, with timing precision measured in minutes across journeys lasting years. Dr. Charlie Kohlhaas, who designed Voyager 1's trajectory, spent years with his team calculating optimal approach geometries using the most powerful computers available in the 1970s. "We were essentially playing cosmic billiards," Kohlhaas recalled, predicting how planetary encounters would redirect our spacecraft across distances of billions of miles with accuracy, requirements that left no room for significant error. The Jupiter gravity assist required Voyager 1 to approach the planet at a precisely calculated distance of 174,000 miles above the cloud tops, close enough to maximize the gravitational acceleration, but far enough to avoid the most intense radiation belts that could damage the spacecraft's electronics. The approach had to be timed so that Jupiter was in exactly the right position relative to Saturn to provide the correct exit trajectory for the Saturn encounter 20 months later. Navigation accuracy during the Jupiter encounter was maintained through continuous radio tracking from Earth. NASA's Deep Space Network measured Voyager 1's position to within a few miles across the 400 million mile distance from Earth, using Doppler shift measurements of the spacecraft's radio signals to determine velocity changes with extraordinary precision. Any deviation from the planned trajectory would have been detected within hours, allowing mission controllers to implement corrective maneuvers. The physics of gravitational assists creates some counterintuitive effects that challenge normal intuition about motion and energy. From the planet's reference frame, the spacecraft approaches and departs with identical speeds. Energy is conserved, and no network is done on the spacecraft by the planet's gravitational field. But from the Sun's reference frame, which includes the planet's orbital motion, the spacecraft can gain enormous amounts of kinetic energy by effectively riding along with the planet's motion around the wowed Sun. Saturn's gravity assist on November 12, 1980, provided Voyager 1 with additional velocity while precisely targeting the spacecraft's trajectory for departure from the solar system. Unlike Jupiter, which accelerated Voyager 1 towards Saturn, the Saturn encounter was designed to bend the spacecraft's trajectory out of the ecliptic plane and toward interstellar space. This maneuver required extraordinary precision to achieve the optimal departure angle while maximizing the velocity gain. The Saturn assist increased Voyager 1's velocity relative to the Sun to over 38,000 miles per hour, fast enough to escape the solar system entirely and continue into interstellar space. This velocity represents the fastest that any human-made object has ever traveled, a speed that will carry Voyager 1 to the nearest star in approximately 40,000 years. The gravity assist provided energy that would have required fuel equal to several times the spacecraft's total mass to achieve through rocket propulsion. The trajectory design for Voyager 1's gravity assists required solving complex multi-body dynamics problems that pushed 1970s computational capabilities to their limits. Mission planners had to account for the gravitational influences of all planets, major moons, and even large asteroids that could affect the spacecraft's path over the years-long journey between planetary encounters. Small perturbations that seemed negligible over short timescales could accumulate into major trajectory errors across interplanetary distances. Computer simulations of potential gravity assist trajectories revealed the existence of launch windows, specific time periods when planetary alignments allowed optimal mission profiles. The launch window for Voyager 1's grand tour trajectory lasted only 20 days in 1977, when Jupiter and Saturn would be positioned correctly for the sequential gravity assist sequence. Missing this window would have meant waiting decades for another opportunity with similar energy requirements. The gravitational dynamics of the outer solar system created additional opportunities for extended missions beyond the primary Jupiter-Saturn encounters. Mission planners discovered that Voyager 1's SAS post-Saturn trajectory could be modified to visit additional planets if the mission were extended, but this would have required sacrificing the close Titan encounter that was deemed scientifically more valuable than additional planetary flybys. Dr. Robert Farquhar, who developed advanced gravity assist techniques, recognized that the Voyager missions were demonstrating navigation capabilities that would enable much more ambitious future missions. Voyager proved that we could precisely control spacecraft trajectories across the entire solar system using gravitational assists, Farquhar explained. This opened the door for missions to multiple planets, asteroid encounters, and eventually interstellar exploration. The success of Voyager 1's gravity assists validated theoretical predictions about celestial mechanics while demonstrating the practical feasibility of using planetary encounters for spacecraft acceleration. The technique became standard practice for subsequent missions to the outer solar system, enabling exploration programs that would have been impossible with conventional rocket propulsion given the weight and cost limitations of launch vehicles. Modern mission design relies heavily on gravity assist techniques that were pioneered by the Voyager missions. The Cassini mission to Saturn used multiple gravity assists from Venus, Earth, and Jupiter to achieve the velocity needed for Saturn orbit insertion. The New Horizons mission to Pluto used a Jupiter gravity assist to reduce travel time by 5 years. The Parker Solar Probe uses repeated Venus gravity assists to gradually approach the Sun's corona. The mathematical elegance of gravitational assists reflects fundamental principles of physics operating on cosmic scales. The conservation of energy and momentum that governs these encounters represents the same physical laws that determine stellar motions in galaxies and the orbital dynamics of binary star systems. Voyager 1's trajectory design demonstrated humanity as growing understanding of how to work with natural forces rather than against them. The precision achieved in Voyager 1's gravity assists required international cooperation in tracking and navigation. Radio telescopes around the world participated in determining the spacecraft's position, while computational resources from multiple institutions contributed to trajectory calculations. The success represented a collaborative achievement that demonstrated how challenging space exploration goals could be achieved through coordinated technical expertise. As Voyager 1 departed Saturn with its trajectory precisely targeted toward interstellar space, the spacecraft's journey became a testament to the power of gravitational assists to enable exploration far beyond what rocket propulsion alone could achieve. The techniques developed for Voyager 1's grand tour trajectory continue to enable ambitious space missions today, demonstrating how fundamental physics can be harnessed to extend humanity's reach throughout the solar system and beyond. The gift of gravity that accelerated Voyager 1 to 15 billion miles from Earth represents one of the most elegant examples of using natural forces to achieve seemingly impossible goals, revealing how understanding and working with cosmic dynamics can enable achievements that far exceed what brute force approaches could accomplish. Chapter 6. silent years after departing Saturn in November 1980, Voyager 1 entered the longest and most challenging phase of its journey, a 30-year traverse through the outer reaches of the solar system, where sunlight is 1,000 times dimmer than at Earth and temperatures approach absolute zero. During these silent years, while the spacecraft received minimal attention from the public and media, Voyager 1 continued operating with remarkable reliability, conducting scientific observations that would prove crucial for understanding the boundary between our solar system and interstellar space. The transition from planetary explorer to interstellar messenger required fundamental changes in how NASA operated Voyager 1. During the Jupiter and Saturn encounters, the spacecraft's every move was monitored by hundreds of scientists and engineers working around the clock to maximize scientific return from brief planetary flybys. But as Voyager 1 headed into the outer solar system's empty darkness, mission operations shifted to a skeleton crew of dedicated specialists who would maintain the spacecraft for decades. Dr. Edward Stone, Voyager's project scientist, described the challenge of maintaining scientific and public interest during the interplanetary cruise phase. We were asking people to remain committed to a mission that might not produce major discoveries for decades. It required a kind of faith in the long-term value of exploration that is rare in our instant gratification culture. The spacecraft itself faced unprecedented technical challenges during the silent years. Voyager 1's radioisotope thermoelectric generators, RTGs, were gradually losing power as the plutonium-238 fuel decayed, reducing electrical output by approximately 4 watts per year. This slow but relentless power decline meant that mission controllers had to continuously prioritize which instruments to operate, gradually shutting down non-essential systems to extend the mission's operational lifetime. By 1990, Voyager 1's power output had decreased enough that NASA was forced to shut down the spacecraft's platform scan system, which allowed the cameras and other instruments to point in different directions. This meant that most of Voyager 1's scientific instruments could no longer be aimed at specific targets, severely limiting the types of observations the spacecraft could make during the cruise phase. But Voyager 1's journey through the outer solar system wasn't entirely silent from a scientific perspective. The spacecraft's fields and particles instruments, magnetometer, plasma detector, cosmic ray detector, and plasma wave instrument continued operating throughout the cruise phase, collecting data about the solar wind and interplanetary magnetic field at distances never before explored by human technology. These measurements revealed that the solar wind, the stream of charged particles flowing outward from the Sun, gradually slows down as it travels farther from its source. At Earth's distance, the solar wind typically flows at 300 to 800 kilometers per second. But Voyager 1's observations showed that by the time the solar wind reaches the outer solar system, it is slowed to less than 100 kilometers per second due to interactions with the interstellar medium. Dr. Leonard Berlanga from NASA's Goddard Space Flight Center, who analyzed Voyager 1's magnetic field data, discovered that the interplanetary magnetic field becomes increasingly turbulent at large distances from the Sun. This turbulence creates complex interactions between solar wind particles and cosmic rays from interstellar space, providing crucial data for understanding how our solar system interacts with the galaxy around it. The most dramatic moment of Voyager 1's silent years came on February 14, 1990, when the spacecraft turned its cameras toward Earth for one final look at the solar system. From a distance of 4 billion miles, Earth appeared as a tiny pale blue dot, less than a pixel in size, suspended in a sunbeam scattered by Saturn's rings. The image became one of the most famous photographs in history, providing a profound perspective on humanity's place in the cosmos. Carl Sagan, who convinced NASA to take the pale blue dot photograph, wrote, "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The image demonstrated how Voyager 1's journey was providing not just scientific data, but philosophical perspective on the significance of human existence in cosmic context. After taking the solar system family portrait, Voyager 1's cameras were permanently shut down to conserve power and protect the instruments from damage by scattered sunlight. The spacecraft would spend the remaining decades of its mission essentially flying blind, navigating by instruments that could sense particles and magnetic fields, but could no longer see the universe around it. The challenge of maintaining communication with Voyager 1 during the silent years pushed NASA's deep space network to its technological limits. As the spacecraft moved farther from Earth, the radio signals carrying scientific data became progressively weaker, requiring increasingly sensitive receivers and larger antennas to detect the transmissions. By the 1990s, Voyager 1's signals were so faint that receiving them required the combined power of multiple 230-foot radio telescopes operating in unison. Mission operations during the cruise phase required extraordinary patience and long-term thinking. Many of the engineers and scientists who had designed and launched Voyager 1 retired during the silent years, replaced by younger colleagues who inherited responsibility for a mission that was older than they were. Maintaining institutional knowledge and technical expertise across decades of personnel changes required careful documentation and mentorship programs. The spacecraft's computer systems, designed with 1970s technology, required increasingly creative programming to maximize scientific return as power levels declined. Mission controllers developed new software techniques that compressed data more efficiently, prioritized the most important measurements, and automated routine operations that previously required human oversight. These programming innovations extended Voyager 1's operational lifetime by years beyond original projections. One of the most remarkable aspects of Voyager 1's silent years was the reliability of its engineering systems. Components designed to operate for 4 years were still functioning perfectly after 2 decades in space, despite exposure to cosmic radiation, extreme temperature cycles, and the gradual degradation that affects all electronic systems over time. This reliability validated NASA's conservative engineering approach and demonstrated the importance of extensive ground testing for long-duration missions. The scientific data collected during Voyager 1's cruise through the outer solar system provided crucial baseline measurements for understanding how conditions change as spacecraft approach the boundary of our solar system. These measurements revealed that the solar wind gradually slows down and becomes more turbulent as it interacts with the interstellar medium, creating a complex transition region that extends for billions of miles. Dr. John Richardson from MIT, who analyzed Voyager 1's plasma measurements, discovered that the solar wind begins showing signs of interaction with interstellar space at distances much greater than previously expected. Voyager 1's cruise phase data revealed that our solar system doesn't have a sharp boundary, Richardson explained. Instead, there's a gradual transition region where solar and interstellar influences compete for dominance. During the silent years, Voyager 1 also served as a pathfinder for understanding the challenges of interstellar navigation. The spacecraft's trajectory was influenced by gravitational perturbations from distant planets and even nearby stars, requiring occasional course corrections to maintain optimal pointing toward Earth for communication. These navigation challenges provided valuable experience for planning future interstellar missions. The thermal environment during the cruise phase created ongoing engineering challenges. With sunlight too weak to provide significant heating, Voyager 1 relied entirely on waste heat from its electronics and RTGs to prevent critical systems from freezing. Mission controllers had to balance power consumption carefully, ensuring that enough electrical current flowed through vital circuits to generate the heat needed to prevent component failure. As the 1990s progressed into the 2000s, excitement began building within the scientific community about Voyager 1's approach to the edge of the solar system. Theoretical models predicted that somewhere beyond 80 astronomical units, the distance from Earth to the Sun, Voyager 1 would encounter the termination shock, where the solar wind abruptly slows down as it collides with the interstellar medium. The silent years tested not only Voyager 1's engineering systems, but also NASA's institutional commitment to long-term exploration. Maintaining funding and technical support for a mission with no dramatic discoveries required convincing administrators and politicians that the scientific value of reaching interstellar space justified the ongoing investment in mission operations. By 2000, Voyager 1 had been operating for over 23 years, nearly 6 times its original 4-year mission duration. The spacecraft was still healthy. Its trajectory was precisely on target for interstellar space, and its instruments were ready to make measurements in a regime that no human technology had ever explored. The silent years were ending, and Voyager 1 was about to begin the most scientifically significant phase of its journey. The 3 decades of cruise through the outer solar system demonstrated that ambitious space exploration requires not just brilliant engineering and scientific planning, but also sustained institutional commitments across timescales that exceed normal human attention spans. Voyager 1's silent years represented a triumph of perseverance and long-term thinking that would soon be rewarded with discoveries that redefined our understanding of where our solar system ends and interstellar space begins. Chapter 7. Message carriers attached to Voyager 1's external structure. Protected by an aluminum cover and designed to last for millions of years, is humanity's most ambitious attempt to communicate with alien intelligence, the Golden Record. This 12-inch gold-plated copper phonograph record contains sounds, images, and information about Earth and human civilization. Selected by a committee led by Carl Sagan to represent the diversity and achievements of our species to any extraterrestrial beings who might discover Voyager 1 in the distant future. The decision to include a message for alien life on the Voyager spacecraft emerged from the success of the Pioneer plaques, metal plates attached to Pioneer 10 and 11 that contained simple pictorial information about humanity and Earth's location. But the Voyager missions offered an opportunity for a much more sophisticated communication attempt, taking advantage of the spacecraft's larger size and more advanced technology to carry a comprehensive introduction to human civilization. Dr. Carl Sagan, who chaired the committee responsible for creating the Golden Record, assembled a team of scientists, artists, and cultural experts to select content that would represent humanity's greatest achievements while being comprehensible to an alien intelligence that might have completely different sensory capabilities and conceptual frameworks. The challenge was extraordinary. How do you explain human civilization to beings who might not see, hear, or think in ways remotely similar to humans? The Golden Record contains 115 images encoded in analog form, ranging from scientific diagrams showing human anatomy and DNA structure to photographs of Earth's landscapes, cities, and diverse cultures. The selection process required making difficult choices about which aspects of human experience were most important to convey, while ensuring that the images could be decoded by beings with sufficient technology to build spacecraft capable of intercepting Voyager 1. The audio portion of the Golden Record includes 90 minutes of music from cultures around the world, natural sounds like ocean waves and bird songs, and spoken greetings in 55 languages. The music selection, curated by renowned ethnomusicologist Alan Lomax, spanned from Bach's Brandenburg Concerto No. 2 to traditional folk songs from Peru, Java, and Zaire, attempting to capture the diversity of human musical expression across cultures and historical periods. Perhaps most poignantly, the Golden Record contains the sounds of a human heartbeat, a baby's cry, and a kiss, intimate audio signatures of human biological and emotional experience that might convey something essential about what it means to be human to any alien intelligence sophisticated enough to decode the record's contents. The technical challenge of creating a message that could survive millions of years in space while remaining decodable by unknown alien technology, required careful consideration of material science and information encoding. The record itself is made of gold-plated copper, chosen for its resistance to corrosion and cosmic radiation. The cover includes symbolic instructions for playing the record, with diagrams showing the proper stylus speed and rotation direction using universal physical constants as reference points. Dr. Frank Drake, who worked with Sega on the message design, developed the symbolic instructions using the hyperfine transition of hydrogen atoms as a universal time and length reference. Since hydrogen is the most abundant element in the universe, any technological civilization would likely understand its properties and could use the hydrogen transition frequency to determine the correct playback speed for the audio content. The Golden Record's cover also includes a diagram showing the position of our solar system relative to 14 nearby pulsars, rapidly rotating neutron stars that emit regular radio pulses. These pulsars serve as a cosmic GPS system that could allow alien beings to locate Earth's position in the galaxy, even millions of years in the future when stellar positions have shifted due to galactic rotation. The selection of human music for the Golden Record sparked intense debate among the committee members about how to represent the diversity of human artistic achievement in just 90 minutes of audio. The final selection included classical pieces by Bach, Beethoven, and Mozart, traditional music from China, India, Peru, and Senegal, American blues and jazz, and contemporary works that demonstrated human musical evolution across cultures and centuries. One notable absence from the Golden Record was popular music from the 1970s. Despite its cultural significance, the committee chose to focus on music with longer historical perspective and cross-cultural appeal rather than contemporary hits that might seem dated or culturally specific to alien listeners. This decision remains controversial among some who argue that excluding popular music misrepresented humanity's actual musical preferences. The spoken greetings on the Golden Record were recorded by United Nations delegates and other speakers representing the linguistic diversity of human civilization. The messages range from simple hello greetings to more complex statements about human hopes for peace and friendship. The selection of languages attempted to represent both widely spoken modern languages and historically significant ancient languages, like Sumerian and Latin. President Jimmy Carter contributed a written message that was printed on the Golden Record's cover. This is a present from a small distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours. This presidential endorsement elevated the Golden Record from a scientific curiosity to an official diplomatic communication from Earth's civilization. The creation of the Golden Record required solving unprecedented challenges in cross-cultural communication and long-term information storage. The committee had to anticipate how human civilization might be interpreted by beings with completely different evolutionary histories, sensory capabilities, and conceptual frameworks. Every choice, from image selection to audio encoding, involved assumptions about what aspects of human experience might be universally meaningful. The time constraints for creating the Golden Record were severe. The committee had less than 6 months to design, produce, and test the records before Voyager 1's launch. This rush timeline meant that many potential improvements and additions had to be abandoned in favor of content that could be reliably produced and tested within the available time frame. Andrew Ruyan, who served as creative director for the Golden Record project, later described the emotional intensity of creating humanity's first interstellar message. We were acutely aware that we were creating something that might outlast human civilization itself. Every decision carried the weight of representing our entire species to the cosmos. The scientific information on the Golden Record includes diagrams of human anatomy, mathematical constants, and basic physics principles that might serve as a foundation for communication with alien intelligence. These diagrams use pictorial symbols and mathematical relationships that that the committee hoped would be comprehensible to any technologically advanced civilization, regardless of their specific evolutionary development. The Golden Record also contains information about human reproduction and child-rearing, including images of pregnant women, families, and children playing. This biological and social information was included to convey essential aspects of human life cycles and social organization that might help alien beings understand human motivations and behaviors. The probability of the Golden Record ever being discovered and decoded by alien intelligence is vanishingly small. Space is so vast that Voyager 1 could travel for billions of years without encountering another technological civilization. But the project's creators understood that the primary value of the Golden Record might be its impact on human consciousness rather than alien communication. Carl Sagan wrote about the deeper significance of creating the Golden Record. The spacecraft will be encountered, and the record played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. The Golden Record project demonstrated humanity's optimistic assumption that intelligence and curiosity are universal characteristics that would be shared by any civilization capable of intercepting Voyager 1. This assumption reflects deeply held human values about the importance of knowledge, artistic expression, and communication across cultural and biological boundaries. As Voyager 1 travels through interstellar space carrying the Golden Record, the message serves as a time capsule of human civilization from the 1970s. Future historians might find the record's content as revealing about human psychology and culture as about our scientific knowledge and artistic achievements, providing insights into what humanity considered most important about itself at the dawn of the space age. The Golden Record represents humanity's first attempt to create a message designed to survive on cosmic timescales. While human civilizations rise and fall over centuries or millennia, the Golden Record is designed to remain readable for hundreds of millions of years, carrying information about human existence long after our species might have evolved beyond recognition or disappeared entirely. The technical specifications for decoding the Golden Record assume that any alien civilization capable of intercepting Voyager 1 would have sophisticated technology and scientific knowledge. But the creators also recognized that such a civilization might have sensory capabilities completely unlike humans, requiring the message to be encoded in multiple formats to maximize the probability of successful communication. Today, as Voyager 1 continues its journey into interstellar space, 15 billion miles from Earth, the Golden Record serves as humanity's first ambassador to the galaxy, a message of friendship and curiosity that represents our species' greatest hopes for contact with alien intelligence, even as it reminds us of our shared humanity and the precious uniqueness of life on Earth. Chapter 8. Communication Challenges. Maintaining communication with Voyager 1 across its 15 billion mile journey represents one of the greatest technical achievements in the history of telecommunications. The spacecraft's radio transmitter generates only 23 watts of power, less than a typical household light bulb. Yet, NASA's Deep Space Network can still detect and decode these faint signals across distances that stretch the fundamental limits of radio communication. Understanding how this communication system works reveals the extraordinary engineering precision required to maintain contact with humanity's most distant messenger. When Voyager 1 launched in 1977, it was designed to communicate reliably across the 900 million miles to Saturn using radio technology that seemed adequate for the planned 4-year mission. But as the spacecraft continued beyond Saturn toward interstellar space, the communication challenges grew exponentially. Radio signals follow an inverse square law. Doubling the distance reduces signal strength by a factor of 4. From Voyager 1's current position at 15 billion miles, its radio signals are 280,000 times weaker than they were during the Saturn encounter. Dr. Dan Goods, who manages communications operations at NASA's Jet Propulsion Laboratory, describes the magnitude of the challenge. Detecting Voyager 1's radio signals is like trying to hear a whisper from someone standing on the opposite side of the United States. The signal is so weak that all the power Voyager 1 has transmitted in its entire 46-year mission equals less energy than it takes to light a flashlight bulb for 1 second. The foundation of Voyager 1's communication system is its 12-foot diameter high-gain antenna, a precisely engineered parabolic dish that focuses radio waves into a narrow beam pointed toward Earth. The antenna must maintain pointing accuracy to within 0.3 degrees across billions of miles, equivalent to hitting a target the size of a tennis ball from a distance of 100 miles. This precision is achieved through a sophisticated attitude control system that uses star trackers and gyroscopes to maintain orientation despite the spacecraft's 38,000 mile-per-hour velocity through space. Voyager 1 transmits on two frequencies, X-band at 8.4 GHz and S-band at 2.3 GHz. The X-band system provides higher data rates but is more susceptible to atmospheric interference, while the S-band serves as a backup that can penetrate Earth's atmosphere more effectively. The dual-frequency approach provides redundancy that has proven crucial for maintaining communication as Voyager 1's transmitter power gradually declines due to aging components. NASA's Deep Space Network, DSN, represents the receiving end of this cosmic communication system, consisting of 3 massive antenna complexes located in California, Spain, and Australia. Each complex features 230-foot diameter radio telescopes that can be combined electronically to create a single, more sensitive receiving system. The strategic placement of DSN sites around the globe ensures that at least one antenna can always point toward Voyager 1 as Earth rotates. The signal processing required to extract meaningful data from Voyager 1's transmissions pushes digital communication technology to its limits. When radio waves from the spacecraft reach Earth, they carry less than 1 quintillionth of the power originally transmitted. Advanced error correction algorithms and signal processing techniques are needed to distinguish the spacecraft's signals from background RADI, noise generated by Earth's atmosphere, cosmic radiation, and human technology. Dr. Charles Elachi, former director of JPL, explains the communication achievement. Talking to Voyager 1 is like having a conversation with someone using a flashlight to send Morse code signals from the moon. Except the moon is 50,000 times farther away and the flashlight bulb is nearly dead. The fact that we can still exchange information reliably demonstrates the incredible precision of both the spacecraft's engineering and our ground-based receiving systems. The data transmission rate from Voyager 1 has decreased dramatically as the spacecraft has moved farther from Earth. During the Jupiter encounter, Voyager 1 could transmit data at rates up to 115,000 bits per second. By the time the spacecraft reached Saturn, data rates had dropped to 44,000 bits per second. Today, Voyager 1 can only transmit at 160 bits per second, roughly equivalent to sending a text message every few seconds. These slow data rates mean that transmitting a single image from Voyager 1 would take over a week if the cameras were still operational. This constraint forces mission controllers to prioritize the most essential scientific measurements, focusing on data from instruments that study particles and magnetic fields rather than attempting to send high-bandwidth observations like images or spectra. The communication protocol between Earth and Voyager 1 operates with delays that challenge normal concepts of real-time interaction. Radio signals traveling at the speed of light take over 22 hours to cross the distance between Earth and the spacecraft. This means that commands sent to Voyager 1 take 22 hours to arrive, and confirmation that the spacecraft received the commands takes another 22 hours to return to Earth. Mission controllers must plan operations more than 2 days in advance and trust that the spacecraft will execute commands autonomously. These communication delays require Voyager 1 to operate with unprecedented autonomy. The spacecraft must detect and respond to emergencies, manage its power systems, and prioritize scientific observations without real-time guidance from Earth. This autonomous operation capability was built into Voyager 1's computer systems during the 1970s design phase, representing remarkable foresight by engineers who anticipated the challenges of deep space communication. The gradual decline in Voyager 1's electrical power output creates ongoing communication challenges. As the spacecraft's radioisotope thermoelectric generators age, they produce progressively less electricity, forcing mission controllers to shut down non-essential systems to maintain communication capability. The transmitter itself consumes a significant portion of Voyager 1's remaining power, requiring careful energy management to extend the mission's operational lifetime. Mission controllers have implemented increasingly sophisticated power management strategies to maximize Voyager 1's communication lifetime. These include reducing data transmission rates, operating instruments intermittently rather than continuously, and heating critical components only when necessary to prevent freezing. Each decision involves trade-offs between scientific capability and mission longevity, with the ultimate goal of maintaining communication for as long as possible. The Earth's atmospheric conditions significantly affect the quality of communication with Voyager. 1. Water vapor in Earth's atmosphere absorbs radio waves at X-band frequencies, degrading signal quality during humid weather conditions. DSN operators must continuously monitor atmospheric conditions and adjust receiving parameters to compensate for weather-related signal variations. Solar activity also influences Voyager 1 communications. When the sun is active, it generates radio interference and charged particle emissions that can disrupt radio propagation between Earth and the spacecraft. Mission controllers must coordinate operations with solar weather forecasts, avoiding critical commands during periods of high solar activity that might interfere with reliable communication. The precision required for maintaining communication with Voyager 1 extends to accounting for relativistic effects caused by the spacecraft's high velocity. As Voyager 1 travels at 38,000 miles per hour away from Earth, its radio signals undergo Doppler shift that must be compensated by precisely adjusting the receiving frequencies at DSN antennas. This relativistic correction becomes more significant as the spacecraft's distance and velocity increase. Advanced signal processing techniques developed for Voyager 1 communications have found applications in other areas of technology. The error correction algorithms, weak signal detection methods, and antenna pointing systems created for the Voyager missions have influenced the development of satellite communications, deep space exploration, and even terrestrial wireless networks. The international cooperation required for Voyager 1 communications demonstrates how ambitious space exploration projects transcend national boundaries. The DSN facilities in Spain and Australia are operated through partnerships between NASA and host country space agencies, creating a global infrastructure that enables continuous communication with interplanetary spacecraft regardless of Earth's rotation. As Voyager 1 continues its journey into interstellar space, communication becomes increasingly challenging, but also increasingly valuable. Each successful data transmission represents a triumph over the fundamental physics of radio propagation across cosmic distances, providing unique scientific information about regions of space that no human technology has ever explored. Dr. Suzanne Dodd, who directs the Voyager interstellar mission, reflects on the communication achievement. Every day that we successfully communicate with Voyager 1 represents a victory over the vast emptiness of space. We're maintaining a technological conversation across distances that are almost incomprehensible.